Hi, everyone. Thank you so much for joining me today. Wow, a full room. That's pretty cool. So welcome to my talk. Today, I'm going to be speaking about practical magic with animations in Compose. My name is Rebecca, and I'm a developer relations engineer at Google. So have you ever been given a motion design and taken one look at it and thought, there's no way I'll be able to implement this? Or you look at inspirational things on Dribbble and you think, I have no idea where to even start with this. I'll tell you a secret. I'm sometimes this person too, and in my journey of learning how to make fun animations, like the ones you're seeing now on screen, I've come to realize that there are some practical steps you can take when trying to break down a complex animation. So in this presentation drawer, we'll use the implementation process of this navigation drawer to understand how to think about animations in general. So let's dive into how we can analyze and implement this animation. After implementing many motion designs, I realized that there are some questions that I keep asking myself, which helps me either pick a specific API or figure out the complex details of an animation. Let's take a look at some of these key principles of animation. The questions that I ask myself is the following. What property am I animating? When does this property animate? Is it on click or is it forever? And how should this property animate? Should it have a bit of bounce or should it be a static animation over time? When I think of these things, it gets a lot easier to break down our animation. So looking at these questions, let's think about the navigation drawer that we are implementing and figure out how to answer them. First, let's talk about what. Most animations are made up of changing different properties or values of a composable on screen. Usually, these are properties such as scale, translation, rotation, alpha, or color. And the best way to approach an animation is to break it down and try to identify individual properties of a composable that are changing over time. Sometimes breaking down an animation is easy because your designer has given you access to the tooling that they've used to implement it. And in this case, you just need to translate it from the tool into code. And you don't need to figure out too much more. But if you don't have this luxury, you might need to analyze a design or video and try and break it down yourself. So in this example, you might notice that we have two different states. And this is helpful for analyzing our animation. By looking at the different settled states that the animation will take and trying to fill in the blanks in between them. The open state of the animation shows the graph content is drawn over our navigation items, and the top content is smaller in an open state, and the corners of the sheet are rounded. In the closed state, there's no sign of this navigation drawer at all. So we can identify that there are at least three properties in this transition that are changing. The translation X, the scale in both the X and Y directions, and the shape corners are getting rounded as it moves into the open state. So we have our app defined with an outer box and two custom composables. Home screen drawer, which is the bottom layer that contains the drawer contents, and screen contents, which will change based on which drawer item is chosen. We also have our drawer state stored in a mutable state. And so with this code, we already have our starting closed state in a correct position. When it is closed, the screen contents draw over the navigation items. And to apply a transition between these two states, we can use modifier.graphics layer. This is a great modifier to use for animations. It allows us to adjust properties such as scale X, scale Y, etc. The other great part about this modifier is that it runs in the draw phase of Compose. So any animation changes here won't trigger a recomposition, as it doesn't need to go through all the phases. In this example, the open state, we set the translation X to the draw width, and the scale X and scale Y to 0.8 to make it a little bit smaller, and the shape of the layer to have a rounded corner shape, which gives us the correct open state. And now, this won't automatically animate between these two states. We've just defined the start and end state of each property. We can see how this looks. We now have the start and end states of the properties, but it's not animating between these two. Great, we know the properties and we know what we're going to work with, and we know that modifier.graphics layer is a great way to go between these two states. So let's talk about when the animation should occur and how we can trigger these animations. So there are a couple of use cases to think about when an animation is normally triggered. For example, an animation can be triggered on a state change, on launch of a composable, infinitely, or with a gesture. So let's talk about each of these different options. On a state change, what does this actually mean? A state change can be something that is driven from a view model or an action that a user takes, for instance, the click of a button or the toggle of a switch, for example. Typically, for these kinds of state change animations, we can use the Animate as State APIs. There are a bunch of built-in options, such as Animate Color as State, Animate Float as State, for instance. And these store and manage the value change for you over time. They are typically used for one-shot animation changes. So let's look at a quick example. In this example, we have a Boolean called clicked. We will adjust this value to true or false, and then using Animate int offset as state, we will change the offset based on if the item is clicked or not. Giving it the new value of the offset, we can then pass this to our modifier to adjust it automatically. For state changes is to use a transition object. This concept allows for coordinated state updates that happen over time. So a quick example of how this works. In this example, we create a transition based on the current state. We then create two properties that will be animated at the same time. The first is the rect size, and the second is the rotation. These will be animated between the two values when the state changes. This would result in the properties being animated at the same time. In this example, the scale and the rotation. Another option for running an animation is on launch of a composable, and when it comes into view. This is typically when you start a screen. For example, if you had a placeholder that needs to be shown before the content is displayed. To start an animation on launch of your composables, we can use Animatable. The animatable object allows us to have control of our animation state, and we can then use launched effect, which will run on its first composition when the key value changes, or when the key value changes. In this example, we could use launched effect side effect to call animate to on our animatable object. And this will invoke our animation when the item is composed for the first time. Another option to animate our content infinitely, or forever and ever, is to use Remember Infinite Transition. In this example, we create an animating scale that the text uses to scale the content up and down for a pulsing animation. And as you can see from this example, the hello text is repeatedly getting bigger and bigger and smaller. The other option for when an animation could be run is as part of a gesture. And this is how this particular navigation drawer is implemented. A gesture drives how this animation is performed. When a user drags on the sheet on top, the content is moved and translated and scaled. But this pattern could be applied to other composables too. So, gesture-based animations are interesting because they need to be interruptible when a touch begins, and they need to continue after a gesture is finished, either decaying or snapping to a certain position. And it also needs to feel like a natural stop. So let's go back to our gesture example, a navigation example. Let's make the transition between these two states animate with a gesture. Let's first start with the gesture processing, and then we can add the animation between the two states. Firstly, let's look at how we can handle dragging of a composable. To create a gesture between these two states, we can introduce an animatable object, translation X, and this will store the value that we're going to translate between the open and the closed states, and we will update this value with a gesture. We can then use this value to set the translation X on the graphics layer, as well as we can use the same value to calculate the scale. In this example, we lerp, or linearly interpolate, between 1 and 0.8, using the translation X divided by the draw width to get a fraction between the two values. Lerp is a way to calculate where a fraction would lie between these two numbers, 1 and 0.8. So if we gave a fraction of 0.5 between these two numbers, it would give us 0.9 as the answer. The next part that we want to introduce is the draggable concept. We will use remember draggable states, and when the delta changes, we'll make sure that the animation snaps to the changed drag amount. We use snap to here because we don't want any animation to actually happen between these two, or when the user is interacting with the gesture on screen. We actually just want the translation Y to be immediately changed. The next step is that we add the draggable modifier to our screen contents composable. And this adds the drag gesture detecting onto our content. We can say that we want the content to be dragged in a horizontal direction only for this interaction. And we pass the draggable state that we've just created into this modifier. Okay, so for a quick visual representation, we can see the start position of our x-axis is 0. And when we drag on the screen, the drag amount is returned in the callback, and the overall translation x value is increased, which we can then use with the modifier.graphics layer to move the composable horizontally. So running this now, we can see that the gesture is changing the translation of the contents on top of the other contents. And this is looking pretty good. You all right? Except there are two issues with this. The first one is that the draw can be dragged completely off screen, and you can't get it back. Kind of a big problem. The second issue is that the draw dragging doesn't continue if I lift up my finger. We only drag when your finger is actually on the screen. It doesn't continue if I perform a gesture and lift up my finger. So, back to our code. To solve the first issue, we can either set the bounds on the animatable object, or we could ignore drag amounts that get us below or above the threshold of what we actually want the user to see. So we will set a bounds on the animatable object. This means that the animation cannot progress past the start and end points of 0 and draw width. It's worth keeping in mind that this caps the animation at these 2 points. So if we wanted to overshoot the animation, maybe with a bit of bounce, we shouldn't use this mechanism, and we should rather instead check these thresholds. Great. So we've solved this first issue. We now have a draw that doesn't completely remove itself from the screen. But now we need to think about what should happen when a user lifts their finger. Ideally, we want the animation to snap to either one of the two states. We don't want an in-between state. We need to take into account the current velocity of the gesture that they're performing on the screen, and use that to determine where the animation should continue to bounce, where it should continue to. Should it go back to the start or to the end? So let's talk about this case of flinging the content. We've already dealt with the drag, but now we want to deal with the fling gesture. And what should happen after a user lifts their finger is called a fling. So back to our code. To do this, we need to calculate the current velocity of the gesture and use it to determine when the drag ends. We first want to create a spline-based DK animation spec. And this will help us calculate the current velocity of the dragging gesture. How fast your finger moves on screen is the velocity of your gesture. And spline-based DK is just a fancy term for a natural-looking animation that'll eventually come to rest at a certain position, given a current velocity. So to use it, we add the onDrag stopped callback onto the draggable modifier. And this gives us the velocity with which the gesture finished, or when the user lifted their finger. In here, we now know that we now have the decay that we created to calculate the decay value, given the current translation x and the velocity of the gesture. This will give us an estimate of where the gesture would naturally stop, given the current velocity. The next bit that we want to determine is the actual target that we want to head towards. We use the midpoint as the decider if it should go towards the end or the start. In our case, if the potential landing point, for example, the dkx is greater than the midpoint, we will target the open state or the draw width. If not, then we'll target the closed state. So let's go back to our diagram. So we understand that whilst the user keeps their finger on screen, we update our animatable object using snap2. And now, when a user lifts their finger, say they perform a fling on the device, we use the current velocity of the gesture to determine the estimated dkx value, or where it would naturally end up. If it reaches past the midpoint, we know we are targeting the draw width as the final destination. In this case, the dkx ends up past the draw width, so we can naturally reach this destination using a decay. We can then call animate decay in this case. If we can't naturally reach this target, say in this example, if we naturally decayed, we'd just end up slightly past the midway of the screen. In this case, we want to call animate2 with our current velocity. And what this will do is it'll take care of increasing the velocity and decreasing it as a natural stop. So back to our code. we now introduce a Boolean called canReachTarget with dk that checks if the dkx is greater than the target x, and the target x is the draw width, or if the dkx is less than the target and the target is 0. So if we can reach the target with a dk, we call animateDK. Otherwise, we call animate2 with the velocity. And finally, we set the current state of the draw to the correct state that it's currently in after the animation. Right, so taking a look at what it looks like now, we now have a draw that snaps to the closest position based on the gesture and the velocity of the initial gesture. And if we fling the draw, we can see it happens a lot faster than without it. We've basically implemented the spec that we had in mind at this point. This logic of dragging and flinging is applicable to many different kinds of animations and interactions that you might want to implement in your app. But for this specific use case, with well-defined endpoints, we can simplify this actually quite a bit. From this example, we've essentially created what AnchorDraggable was designed for. It's very similar to the draggable modifier, but it allows you to specify anchor points for the drag gesture. It's part of Foundation and was added in Compose 1.6.0 Alpha 3. In this example, our anchors would be the open and closed states in the draw width, the open and closed states, 0 and the draw width. So let's simplify our code quite a bit and replace the logic with the AnchorDraggable components instead. So first we define our anchors, draggable anchors, open at draw width and closed at 0. Next, we create the draggable state with an initial value of closed and passing in the anchors, setting the positional threshold to the midpoint of the drag. We then change our modifier to use AnchorDraggable instead of draggable that we created before. And we use the state.require offsets to get the translation x of the drag gesture. And this gives us a pretty similar interaction to what we just manually defined before, in a more generic way. So we have our animation defined, and we're pretty happy with it at this point. But what if we wanted to make it a little bit more fun? Maybe add a little bit more bounce. The last question that we need to answer when we're looking at any kind of animation is how our animation should be performed. We should be thinking, how playful should our animation be? Or how long should an animation take in milliseconds? Once we've figured out how our animation should play, we can take a look at the different APIs that we have to help us achieve this. Looking at an example using Animatable, in this example, we are just animating from 0 to 360 on launch of a screen. We have our animation set up and ready to go, but we want to customize how this should run, not when or just what it runs on. This brings up talking about animation specs. Each animation is controlled by an animation spec, which stores information about the type of transformation that's going to happen. For example, if we are transitioning between 2 integers or 2 floats and its configuration. The following are the animation specs that are available at the moment: tween, spring, snap, keyframes, and repeatable. The default that most Compose animations are using is a spring spec, and we'll get into why in a bit. But let's talk a little bit about tween specs. This spec allows you to specify how to animate between 2 values. Tween is just a shortened version of the word between. There's nothing fancy here. This spec is useful for when you want to set a duration in milliseconds for how long your animation should take. In this example, we've set it to take 300 milliseconds. So this is great to be able to customize. But what if we wanted to change how the value transforms between 0 and 300 milliseconds? Enter the concept of easing. Easing describes the rate of change of your animation over time. Easing is an interface that takes a fraction and produces another value. These easing functions are then used by tween to determine where a value should be in its execution. By default, tween transforms your value using a built-in spec called fast out, slow in easing. Let's learn a little bit more about linear easing, though. This is when you transform your values linearly. There's no acceleration or deceleration. In this example, when we change the easing curve to linear easing, the animation would run as follows. At 0 milliseconds, the x offset would be 0, and exactly midpoint, it would be exactly halfway. And at the end of the animation, 300 milliseconds, the x offset would be at its final destination. Another implementation of easing that looks a little bit more natural than linear is cubic Bezier easing. This allows you to follow a Bezier curve, where you can specify control point 1 and control point 2, these 2 points will determine the curve that the animation will follow. The example on the right has the easing curve defined by these 2 points that the animation will go between. And a new addition to the APIs is the ability to create a custom easing curve based on a path. We provide a path between 0 and 1, and in this example, we combine together 2 cubic curves to form a path that the animation will follow. A good example for how to think about easing and what makes a good easing function is like a roller coaster. A good roller coaster doesn't travel at the same speed all the time. At portions of the ride, you're going faster, and at the end, you're hopefully coming to a stop. Similarly, with easing functions, using a linear function doesn't always look and isn't such a great experience. It's jarring and, dare I say it, a little bit boring. We can then use these easing functions that are specified, easing curves, by defining the easing parameter on the tween spec. So this diagram shows the difference between applying different easing functions, linear and fast out, slow in easing, applied to the same animation. As you can see, there's a big difference between the two. Fast out, slow in seems a little bit more natural than a linear curve. So there are a bunch of built-in easing functions for you to use in Compose that should take care of most of your requirements. But if they don't, there are plenty of ways to define your own. Okay, so we've talked a lot about tween and setting your custom easing spec. But at the start, I mentioned that Spring is a little bit better and it's used by default. So why is this? Well, Spring animations are actually physics-based animations based on stiffness and a damping ratio. They generally look and behave in a more natural way than tween animations would. Let's take a look at how Spring animations work and then understand why. Let's look at the problem when using tween compared to Spring. Specifying a duration for an animation doesn't always work as you'd expect. For example, if we have 2 boxes, and the first one only needs to travel a smaller distance than the other, but applying the same duration to both of them produces a very different feel for both of them. So what if your device is larger? Say you have a very large tablet, and you're animating from the top to the bottom of the screen. You'd see a massive difference in the animation between these 2 devices, as both of them need to complete the animation in the set duration that you've given them, but with variable distances between them. The same can be said for interrupting an animation. For example, when I interrupt a tween animation and set a new target value, using tween doesn't work as fluidly as using Spring, as Spring animations take into account the current velocity of your gesture, of your animation, making it feel more natural. And you can see from these 2 videos, the first is using the same duration for each of the same changes in position here. It just doesn't look as natural compared to the Spring version. Now, if we look at what we can configure with a Spring, we can set 2 different things, stiffness and damping ratio. This allows us to customize how bouncy our animation should appear and how long the animation should take to come to rest. And as you can see, you can get very different looking feels from your specs from this. Alternatively, if it's a bit more of a serious app, you probably don't want to set such a bounce, but you can still use springs to communicate this. You don't need, a Spring animation doesn't necessarily mean bounce. So here's an example of different Spring configurations. Looking at each of these, you can see how applying a different spec configuration can communicate a completely different look and feel to your app, where the bouncy spec looks more playful, but you can get just as nice of an animation using a gentle spec defined with springs. Okay, so back to our example. What if we wanted this particular example to be more bouncy? We can change this animation spec to be using a Spring animation and remove the decay to get a bit more of a playful effect on the app. Okay, so we've covered some of the more basic APIs and principles of animations. And whilst most animations can be built from the ground up using simple primitives, luckily you don't always need to build from the ground up. There are some predefined composables that are built into Compose that take away a lot of this work for you. The first one is animated visibility. It allows you to toggle the visibility of a composable with a pretty animation. For example, when used within a column, it'll automatically be removed if applying animated visibility, it'll be removed with a nice animation. Another built-in example is animated content. And it's a built-in composable that allows for animations between different composables. It allows you to customize the transition between these 2 states, customize the Z order of the animation. For example, we can typically wrap when conditionals with animated content for more seamless transitions. In this example, we wrap our content in animated content and it will provide a more seamless transition. Our transition between these different composables in this example are fading and scaling between each other, which looks a lot better than just an instant transition. There are plenty more built-in composables that you can use, and if you're looking for a quick guide on getting started with the animations in Compose, feel free to take a look at this link. Right, on to the last section of this talk. How do I pick the correct API for the job? When thinking of choosing an API, there are many different options to pick from. And looking at the docs, you might be a little bit overwhelmed. And whilst over time you'll eventually get a feel for what API can help you, we do have many options to think about. Pretty much most animations can be built using a single animatable or using an animate suspend function, as we've explained already, but there are many more handy options that you can use for your specific use case. We've recently released a new version of the decision tree diagram for Compose animations. This should help you get started with thinking about which API would suit your use case. It's not meant to be strictly followed, as many APIs can be retrofitted for different purposes, but it should help you narrow down your options and think about which questions to ask yourself when implementing. For example, if we're thinking about animating the text color when an error occurs in our UI, let's follow this diagram to see where we would end up. First, we ask ourselves the question, is our animation like art? Does it have a lot of visuals and imagery that we are animating on screen? In this case, no, because it's just text. Then, does our animation need to repeat forever? In this case, no, it doesn't. It gets updated based on the state, if we are in an error state or not. The next question is this a layout animation? In this case, no, because it's the color of a composable, not a layout property. And next, we ask ourselves, do we need to animate multiple properties? In this case, no. It's just a single text color that's being animated. And does the animation have a set of predefined target values? In this case, yes, because we have an error state and a non-error state, red and black. And also, in this case, we also have text. We are also using text. So we should also set the text motion animated on the style property. The full diagram can be found at this link, and this should help you get started with thinking about which animation API to choose whenever you are getting started. So in summary today, we've covered a bunch of concepts for animations. But most importantly, you should try to analyze your animation with what, when, and how in mind. We also learned that gesture-driven animations are typically made up of two parts, flinging and dragging on screen, and how to handle these situations. And finally, using the built-in components you should use the built-in components to make your common animations easier. And if you don't know which animation API to use, you can use the decision tree diagram to help you decide. And that's it. Wait, what did I hear? You wanted more? Let's do a quick bonus animation then. Let's talk a little bit about image vectors. And you might remember animated vector drawables. What if I told you that you don't need to create your micro SVG animations in XML file either? Let's take a look at this fun example of a jellyfish. Everyone's app contains jellyfish, right? Would you believe me that this jellyfish is actually rendered in SVG, and we can break this down and manipulate it with code? Let's take a quick look at how we can do this. If we inspect an SVG file for what this jellyfish contains, we can see that there are paths defined in this SVG for each bit of the image. We can take these path commands defined inside the SVG and build it up in code in a similar way. For those unfamiliar, a path is just a set of mathematical commands instructing how to perform how to build up your item on screen. For example, inside this path string, we can see that there are letters. They correspond to a certain command that should be performed, such as a line to a certain point or a cubic curve, etc. So we want to render this vector programmatically in code. It's worth noting that we could use Lottie, or we could load this up with AVDs if we have. But for the sake of this example, we're going to be rendering this with image vectors. So to do this, we first take the individual parts that are defined in the SVG. We then create a vector using Remember Vector Painter, and we create an image composable, passing in the image vector that we are now creating. We then add the path to the image vector by creating these groups that take the path data and the color for it. We repeat this process for each part in the SVG. And we now have a vector that is rendered in code instead of being loaded up from disk or from assets. This is super useful because we can actually now animate parts of the image vector on screen. So using the principles that we've just learned throughout this talk, is we can now see and analyze this animation and decide which properties are changing over time. We can see that the whole jellyfish moves up and down infinitely over time. So we should use translation Y and remember infinite transition. And the eyes blink when you tap on them. So we should animate the scale and alpha using animatable to have fine control over these touch events. Missed a few steps there. Okay, let's look at how to implement this blinking animation. We can create two animatable objects, one that represents the alpha and the other one that represents the scale. Then we can create a suspend function that we will then call when the jellyfish is touched. We call launch, animating the alpha from 1 to 0, and then back from 0 to 1 after 150 milliseconds. The way that we are calling animate2 here means that these two calls will run one after the other. The next part is that we call launch again in this coroutine scope. This will ensure that the animation is run at the same time as the other launch block. And the scale is what we will animate here. We will animate from 1 to 0.3 and back again. Great, so we've got our two variables, but now we can actually apply them to this vector. First, we change the scale Y of the eye. So we apply the animation value to the scale Y property of this eye group. We then apply the animation value to the path fill alpha as well. The same can be done for the translation Y variable, applying a translation over time with an infinite transition. And there we have a blinking jellyfish. And that's all. Building animations in Compose should be fun. And if you have any ideas or feedback on what we could improve, please feel free to find me after the conference. Thank you so much for listening.